The sunlight warming your face right now began its journey in the sun's core before human civilization existed. In that brief flicker against your skin lies a story older than cities, older than language. Have you ever wondered what secrets a single sunbeam carries? Each moment under this light connects you to a cosmic saga spanning billions of years. Feel the warmth and imagine photons forged in unimaginable heat and pressure. This golden glow is more than daylight. It's the echo of ancient stellar cataclysms that gave birth to our very solar system. Billions of years ago, there was no sun. Instead, a vast cloud of gas and dust drifted through empty space. That cloud was seeded by the ashes of long-dead stars, massive supernovas that scattered stardust like cosmic fireworks. Gravity began its slow, inexorable pull, drawing particles together. As the cloud condensed, temperatures and pressures climbed. Over time, this spinning nebula formed a dense core at its center. Yet the real drama lay hidden, deep within. A brewing furnace of unimaginable intensity waited to ignite the fusion that would light our sky. As gravity continued its reign, the nebula's center grew hotter and denser. Temperatures soared past millions of degrees. Pressure built to crushing levels. Finally, in that compact heart, hydrogen atoms fused, igniting a chain reaction to define the sun's life. 4.6 billion years ago, this moment transformed a glowing ball of gas into a mighty star. The core reached roughly 27 million degrees Fahrenheit. Hydrogen nuclei slammed together, forming helium and releasing vast energy. Each second, the newborn sun converts about 4 million tons of mass into light and heat. It was the birth of endless daylight. But the fusion furnace was only half the story. Deep within the core, photons were born, particles of light carrying raw energy. These newborn photons faced a chaotic gauntlet. They collided with protons, electrons, and atomic nuclei, scattering in every direction. Rather than streaming outwards, they bounced again and again, trapped in a fiery labyrinth. This random walk slowed their escape to a crawl. Despite moving at light speed between collisions, constant redirection meant reaching the surface could take tens of thousands of years. Each photon's journey was an epic struggle through turbulent, superheated plasma. The sun's interior is divided into zones. First comes the radiative zone, spanning nearly 70% of the distance from core to surface. Here, photons endure countless interactions, each collision shifting their energy spectrum. This region demands tens of thousands of years of wandering. Beyond it lies the convective zone, where hotter plasma rises and cooler plasma sinks in gigantic currents. Photons hitch rides on these churning flows, carried closer to the surface. Complex magnetic fields twist around them. The environment resembles a boiling ocean of fire, a dynamic realm where light battles its way to freedom. At last, a photon emerges at the photosphere, the sun's visible surface. In that instant, the ancient prisoner finds a narrow window to escape. It bursts into space, joining an invisible torrent of other photons. From collision to release, a single photon might have wandered for 100,000 years. Yet once free, it embarks on a sprint across the void at nearly 186,000 miles per second. The sun radiates this outpouring continuously, sending a flood of light across the solar system. Our planet bathes in this radiation, powered by processes forged long before any creature walked Earth. Next comes the briefest leg of the voyage. Once a photon escapes, it travels approximately 93 million miles to Earth in just 8 minutes. That fleeting journey compresses cosmic history into a blink. When you step outside at dawn, the light you see began its epic trek centuries of eons ago. Here lies a paradox. What feels immediate is profoundly ancient. Each sunbeam is a time capsule carrying relics of the sun's fiery heart. In that 8-minute sprint, the photon passes planets, meteoroids, and invisible solar wind. It weaves a path shaped by gravity and magnetism before slipping through our atmosphere. While photons race toward Earth, another frontier of solar science unfolds. Since its launch in 2018, NASA's Parker Solar Probe has plunged closer to the Sun than any spacecraft before. It braves fierce heat and radiation, orbiting through the corona, where plasma temperatures soar to millions of degrees. By measuring magnetic fields and charged particles, Parker explores how energy transfers from the Sun's surface into the solar wind. These solar breezes stream past planets, sometimes buffeting Earth's magnetic shield and sparking brilliant auroras. Understanding this dynamic environment is critical for protecting satellites, astronauts, and power grids. Parker's daring mission unveils the forces that also shape the Photons' epic journey, deepening our grasp of the star that sustains us. Beyond light, the Sun breathes out charged particles in a constant flow known as solar wind. These particles travel at millions of miles per hour, shaping the heliosphere and interacting with Earth's magnetic field. When strong solar storms erupt, the resulting geomagnetic disturbances can disrupt communication networks and power grids. But they also produce awe-inspiring auroras near the poles, painting the sky with curtains of green and purple light. Research from Parker reveals the mechanisms powering solar storms and helps forecast eruptions, safeguarding our technological civilization. This phenomenon reminds us that the Sun's influence extends far beyond daylight, forging an ever-changing space environment around us. Consider the massive stars whose supernovae sowed the seed material for our Sun. These titanic explosions forged elements heavier than iron and oxygen, birthing gold, uranium, and every atom of carbon that forms the backbone of life. Over millions of years, interstellar turbulence mixed this stardust with hydrogen and helium in a vast nebular cloud. Gravitational collapse then sculpted planets and asteroids from that primordial soup. Today, meteorites carry microscopic grains of this ancient dust, preserved like time capsules from the galaxy's youth. Scientists study these cosmic grains to uncover the Sun's earliest history and trace chemical pathways of planets. In laboratories on Earth, researchers extract isotopes from these grains, performing precise age measurements that clock when they formed. By analyzing chemical signatures, scientists reconstruct temperature and pressure conditions in the solar nebula. Some grains even predate the Sun's ignition, carrying records of ancient supernova shockwaves. These microscopic minerals offer a tangible link to the processes that shaped our planet's habitability, including the delivery of water and organic molecules. This multidisciplinary work connects astrophysics, geology, and chemistry, illustrating the deep interdependence of cosmic and terrestrial evolution. Human ingenuity has harnessed sunlight's power, converting ancient photons into electricity. Solar panels capture the same cosmic travelers born in nuclear fusion. When sunlight strikes photovoltaic cells, electrons are excited, generating clean energy that lights our homes and powers our devices. This technology embodies our connection to stellar processes. Each solar farm taps into a furnace powered by 30 million degree nuclear fusion. Understanding sunlight physics fuels curiosity and drives sustainable solutions. It reminds us the Sun's legacy can illuminate tomorrow as brightly as the past. When you next step into daylight, pause for a moment. Let the Sun's warmth remind you of a journey that spans galaxies and eras. Every photon you feel has braved unimaginable forces, danced through boiling plasma, and crossed the vast emptiness of space. Each ray is a testament to the power of gravity, fusion, and time itself. This simple warmth ties you to a story as old as the universe. It is both humbling and exhilarating to know we share our days with ancient cosmic travelers.